Pump performance characteristics. Pump manufacturers run tests to determine performance data for their various types of pumps. The overall efficiency of a pump can be computed by comparing the hydraulic power output of the pump to the mechanical input power supplied by the prime mover. Overall efficiency can be broken into two distinct components called volumetric efficiency and mechanical efficiency. Volumetric efficiency. Volumetric efficiency indicates the amount of leakage that takes place within the pump. This involves considerations such as manufacturing tolerances and flexing of the pump casing under design pressure operating conditions. Volumetric efficiency is equal to the ratio of actual flow rate produced by pump to theoretical flow rate pump should produce, QA by QT. Volumetric efficiencies typically run from 80% to 90% for gear pumps, 82% to 92% for vane pumps, and 90% to 98% for piston pumps. Note that when substituting efficiency values into equations, decimal fraction values should be used instead of percentage values. For example, an efficiency value of 90% would be represented by a value of 0.90. Mechanical efficiency. Mechanical efficiency indicates the amount of energy losses that occur for reasons other than leakage. This includes friction in bearings and between other mating parts. It also includes energy losses due to fluid turbulence. Mechanical efficiencies typically run from 90% to 95%. Mechanical efficiency is the ratio of pump output power assuming no leakage to actual power delivered to pump. Using English units and horsepower for power yields, mechanical efficiency is equal to P into QT by 1714 whole divided by TA into N by 63,000. In metric units using watts per power, mechanical efficiency becomes P into QT divided by TA into N, where P is pump discharge pressure in pounds per square inch or Pascal, QT pump theoretical flow rate in gallons per minute or cubic meter per second, TA actual torque delivered to pump in inches pound or Newton meter, and N pump speed in RPM revolutions per minute or radians per second. Overall efficiency. The overall efficiency considers all energy losses and hence is defined as follows. Overall efficiency is equal to actual power delivered by pump divided by actual power delivered to pump. The overall efficiency can also be represented mathematically as follows. Overall efficiency is equal to volumetric efficiency multiplied by numerical efficiency, which becomes QA by QT into P into QT by 1714 whole divided by TA into N by 63,000. Overall efficiency becomes actual horsepower delivered by pump divided by actual horsepower delivered to pump, which is equal to P into QA by TA into N, which is actual power delivered by pump to actual power delivered to pump. Note that the actual power delivered to the pump from a prime mover via a rotating shaft is called brake power, and the actual power delivered by a pump to the fluid is called hydraulic power. Pump selection factors. Pumps are selected by taking into account a number of considerations for a complete hydraulic system involving a particular application. Among these considerations are flow rate requirements, gallons per minute, operating speed, revolutions per minute, pressure rating, pounds per square inch, performance, reliability, maintenance, cost, and noise. The selection of a pump typically entails the following sequence of operations. First one, select the actuator, hydraulic cylinder or motor that is appropriate based on the loads encountered. Second one, determine the flow rate requirements. This involves the calculation of the flow rate necessary to drive the actuator to move the load through a specified distance within a given time limit. Third one, select the system pressure. This ties in with the actuator size and the magnitude of the resistive force produced by the external load on the system. Also involved here is the total amount of power to be delivered by the pump. Fourth one, determine the pump speed and select the prime mover. This together with the flow rate calculation determines the pump size, which is volumetric displacement. Fifth one, select the pump type based on the application, gear, vane or piston pump, and fixed or variable displacement. Sixth one, select the reservoir and associated plumbing including piping, valving, filters and strainers and other miscellaneous components such as accumulators. Seventh one, consider factors such as noise levels, horsepower loss, need for a heat exchanger due to generated heat, pump wear and scheduled maintenance service to provide a desired life of the total system. Eighth one, calculate the overall cost of the system. Normally, the sequence of operation is repeated several times with different sizes and types of components. After the procedure is repeated for several alternative systems, the best overall system is selected for the given application. This process is called optimization. It means determining the ultimate selection of a combination of system components to produce the most efficient overall system at minimum cost commensurate with the requirements of a particular application.